Hello, my name is Adrian Camiso. For my spacecraft design project, I decided to design an atomic force microscope. So I'll give you a quick overview of what an atomic force microscope is before I jump into my design. An atomic force microscope is a type of microscope that measures the height map of a specimen based on the deflection of a needle as it's scanned across a surface. So quick overview, there are a couple different types of atomic force microscope. There's the contact mode, non-contact mode, and tapping mode. Contact mode is usually for larger scales, doesn't work well in small sample sizes because it can damage the sample. Non-contact mode is known to work at very small scales where electrostatic forces come into play. And then the last method, which is the method I chose, is known as tapping, and this is where the microscope measures a change in oscillation of the needle to determine the height of the specimen. So my design consists of 5 different components. The first component is the motion platform. For my purposes, I was able to commandeer my 3D printer to perform this task. The second component is the oscillation circuit. So this circuit runs the audio signal from the Raspberry Pi through an op-amp, which then goes to a speaker and is conducted into the needle tip. Next, there's the deflection measurement circuit. This uses an analog to digital converter as well as a magnet and Hall effect sensor mounted to the needle so that the sensor can detect how much the needle is deflected at any given point. And then this is fed into the Raspberry Pi through the serial peripheral interface. Then there's the needle assembly itself. So this is just a 3D print that houses all the different components. You can see the speaker. There's a screw that conducts the speaker to the flexible needle component and a component that holds the Hall effect sensor. Finally, there's the frequency analysis script. This is the code behind the whole microscope that runs in the background and analyzes the frequency changes in the needle to produce a height map. So next I'll run through an example scan so you can see how the microscope works. This here is my main script that runs all the processing for the scan. So if we move down to the user input section, this is where the dimensions of the scan can be set in millimeters and the scan resolution. That'll be the distance between each measurement point. And there are some other tuning parameters in here as well. So now if we run the script, a program will connect to the printer using the Pronsel software. Then it'll remind you that the scanning head needs to be removed so that it can perform the homing motion. Once the printer is done homing, we can insert a specimen to be scanned. In this case, I'll be using a small circuit board. Using the manual controls on the printer, you can then move the needle head to the desired start location. Then the script will perform a circle around the scanning area to confirm with the user that this is the desired scanning area. Now all that's left is to confirm with the software that we want to perform the scan. So you'll see the tip starts to oscillate, and then after a couple seconds the head will start to creep across the surface, taking a measurement at each point determined by the resolution. Because a high-resolution scan takes quite some time, on the order of an hour, I decided to lower the resolution for this example. So what you're seeing here at the end is just at the very top right corner. Here are some higher resolution scans of the back of a Lego brick and a higher resolution scan of that circuit board that I was scanning earlier. I want to say thank you for organizing this project, and I'll leave you with some slow motion video of the needle tip oscillating.